deep within the constellation Taurus, some 6,500 light-years from Earth, we find the magnificent Crab Nebula, the principal item in the Messier catalogue of night sky objects astronomers use today. First spotted back in the mid-18th century, it didn't take astronomers long to link this cloud of interstellar gas to a great supernova explosion, which was known to have illuminated the sky in the same spot around 700 years before. Standing out as a source of intrigue ever since, the Crab Nebula is one of the most well-known and extensively studied objects in the sky, and has continued to surprise astronomers as the technology to probe it has improved. By the late 1960s, the advent of radio astronomy had revealed the Crab Nebula to be hiding another object left over from the supernova, a considerably smaller, yet far more extreme type of object, a rapidly rotating neutron star. Neutron stars are the final form of matter before it turns into a black hole, and they have played an instrumental role in lacing our galaxy with the ingredients for life. And so today, we will revisit these mind-bending objects with our focus on the insane power of pulsars. Neutron stars do not arise from bodies like the Sun. When a Sun-like star nears the end of its life cycle, it swells up to red giant stature and ultimately falls apart, exposing its core to form a compact white dwarf. But for much larger, less stable stars, at least tenfold the mass of our Sun, a different fate lies in store. Instead of coming unbound, these massive stars eventually run out of fuel and collapse under their own tremendous weight, their outer layers compressing the inert iron core before bouncing back and exploding in a blinding supernova event. What comes next depends on the mass of the bygone stellar core in question. If it weighed more than thrice that of our Sun, then nothing will be able to hold back a runaway gravitational collapse which continues to compress matter beyond its Schwarzschild radius, forming an event horizon and ultimately a black hole. But below this critical mass threshold, the collapsing core will not be heavy enough to overcome its matter's last line of defense. As molecules are squashed together, temperatures climb so high that they eventually begin breaking apart the structures of atoms, converting the core's iron mass into a dense soup of subatomic particles. Free-roaming, negatively charged electrons are crushed into the exposed nuclei of atoms, where they merge with positively charged protons to yield abundances of neutral neutron particles. Eventually, the core will be just a fraction of its original size, jam-packed and bursting with excess neutrons. And this is where the real fight back against the gravitational collapse begins. Because no two neutrons can occupy the same quantum state in close confinement, they constantly fluctuate and switch between states in the presence of other neutrons, yielding a degeneracy pressure that resists their compression. And with a helping hand from the same nuclear forces holding up the structures of atoms, a sufficient outward pressure is exerted that halts the collapse when the body is no more than about 25 kilometers wide, its contents packed as tightly as an atomic nucleus. The star's outer layers then ricochet and explode in a supernova, leaving only the leftover neutron star, the final form of matter before it collapses into a black hole. They have all the mass of up to 2 solar systems packed into a sphere no larger than a city such as Boston, Frankfurt or Cincinnati, and this incomparable compression is the driving force behind some of the most extreme physical phenomena we've ever seen in space. On the outside of a neutron star, a rigid, tortured shell of superheated iron encloses the hellish processes unfolding below. Its gravitational influence so strong that the escape velocity needed to leave is above half the speed of light. So great, in fact, that even time is stretched and dilated, the same way it is by the gravity of a black hole. These torrid iron shells sizzle at blistering temperatures for hundreds of millions of years on end, with the closest known neutron star to Earth radiating at almost 500,000 Kelvin. But even this mind-melting temperature pales in comparison to the poorly understood environment playing out inside the neutron star. Undercutting its crust is a crystalline mantle of so-called nuclear pasta, long strings of squashed neutron-degenerate material in various intermediary states before its true form, bulk neutronium, which is theorized to exist in a superfluid state at the core. The swirling of this superfluid, along with the rotational velocity of the body, supplements the neutron star's extraordinary, unparalleled magnetic field, amplified to hundreds of billions of times the strength of Earth's by the immense compression of the progenitor star. Indeed, neutron stars are the most powerful magnets in the universe, exhibiting a broad range of electromagnetic phenomena as a result. This enables them to stand out among the many billions of stars in our galaxy, and sometimes from other galaxies entirely, but rarely in the visible spectrum of light. In fact, neutron stars are most prominent in the sky when searching in radio, X-ray or gamma-ray frequencies, and the spectra of these objects can tell us a great deal about the type of neutron star and the things that surround it. As a neutron star rotates, particles caught up within its magnetosphere ride along the lines of flux as they are transported towards the polar caps. But when they arrive, they are radically repelled and blasted out into space at relativistic velocities, their acceleration causing them to emit synchrotron radiation, which is most prominent in radio wavelengths. And because these polar caps are not aligned with the neutron star's rotation, their movement swings the funnel-like beams of radio energy around the circumference of the body like a lighthouse, sometimes sweeping in the direction of Earth. These signals often reach our planet on a strikingly periodic basis, detectable as a series of evenly spaced pulses. That's how we detected the first real evidence of neutron stars in the wild, through their pulsar beams of radio emission, the likes of which began cropping up in the sky as radio astronomy developed in the late 1960s. The first to chance upon one of these signatures was the postgraduate Cambridge student Jocelyn Bell Burnell, when in 1967 she uncovered a stream of galactic pulses occurring 1.3 seconds apart with pinpoint precision. Her discovery initially baffled scientists, with some speculating it to be an artificial, engineered communication from another intelligent species in the galaxy. But by the end of the decade, a handful of similar radio sources, like the one emanating from the heart of the Crab Nebula, were weighing in favour of a more natural, shared origin for these objects. Rotating far too quickly to be a white dwarf, theoretical neutron stars soon emerged as a leading candidate for the source of these rapid radio beacons. And since then, we've catalogued more than 3,200 of them right across the galactic disk, the majority of which are radio pulsars. And given the number of supernovae estimated to have occurred over the Milky Way's 13 billion year lifespan, there may be as many as 1 billion of these extreme, irradiating stellar cores lurking within the fields of our galaxy, and all galaxies beyond for that matter. However, most of these will be ancient and will have cooled down and slowed their rotations to the point of becoming undetectable. Radio pulsars are usually at their hottest and spinning their fastest within the first million years of their inception from a supernova. If a pulsar exists in isolation without a significant stellar companion, then it can only lose its rotational momentum over time, as it radiates gravitational and electromagnetic energy in a process known as spinning down. As a pulsar spins, its magnetic field lines drag on their surrounding space and decay, transferring the pulsar's kinetic energy into electromagnetic radiation. This process is responsible for many of the most characteristic neutron star emissions, from longer wavelength radio pulsars to more energetic short wavelength X-ray and gamma-ray emitters. But for the latter, a neutron star generally needs to be able to gain energy from a donor object, namely from a companion star within a binary system. If a pulsar hosts a stellar companion, whether it's a white dwarf or red giant, then swathes of ejected material will be cast into space from the partner and swept up into an accretion disk that surrounds the neutron star. Particles are then fed from the inside of this disk onto the pulsar's surface, both growing its mass and increasing its rate of rotation, by packing it more tightly and transferring angular momentum, a process known as spinning up. This type is known as an accretion-powered pulsar or an X-ray pulsar due to their prominence in the X-ray bands. As swirling, invigorated electrons are captured from the accretion disk and tethered within the magnetosphere, they decelerate to emit high-energy X-rays from auroral-like hotspots around the pulsar's polar caps. These X-ray emissions are spun around to yield a signal much like a radio pulsar. But unlike radio pulsars, which can only spin down, X-ray pulsars have been seen speeding up, slowing down, and even remaining relatively consistent in their rates of rotation. If their companion is a small red or white dwarf star, or perhaps a sun-like star, then we call it a low-mass X-ray binary. Alternatively, a massive, unstable red or yellow giant as the donor makes for a high-mass X-ray binary. In both cases, however, abundant energy is stripped from the companion to spin these pulsars up to some truly jaw-dropping velocities of hundreds of revolutions per second. And when a pulsar's rotation period is less than 10 milliseconds, or more than 100 spins per second, we call it a millisecond pulsar. Also known as recycled pulsars, millisecond pulsars are the fastest type of neutron star, having been spun up by accretion to a substantial portion of the speed of light, producing an incredibly regular and periodic signal that makes for a highly sensitive indicator of the pulsar's surrounding environment. These signals are so frequent, in fact, that even the gentle tug of asteroids on a pulsar can be reflected in its measurements of Doppler shift. Even now, the first 2 exoplanets ever discovered in 1992, which were found around the millisecond pulsar B1257+12, remain the smallest known extrasolar bodies to this day, with masses and diameters comparable to the Moon. The first millisecond pulsar, B1937+21, was discovered a decade earlier. At a rate of 641 revolutions per second, it persists as the second fastest of about 200 recycled pulsars identified in the 4 decades since. Around 130 of these are found within globular star clusters, containing tens or even hundreds of thousands of bunched up stars, generally less than a light year apart from one another. The high stellar density of these environments lends itself to binary systems, filled with ancient, massive stars, many of which will have transitioned into pulsars long ago. The clusters Terzan 5 and 47 Tucanae in particular boast the highest numbers of known millisecond pulsars, with 37 and 22 respectively. And the former, Terzan 5, also hosts the current fastest known millisecond pulsar as of the making of this video, J1748-2446 AD. With a staggering frequency of some 716 Hz, this object spins some 43,000 times per minute, its equator barreling through space at a quarter the speed of light. But even at this insane rate, the magnetic field of the beast would still not be radiating at its maximum possible potential, because the rate of a neutron star's rotation is not the primary factor determining its magnetic field strength. That depends more on its age and the type of star that came before, like HD 45166, a recently discovered so-called massive magnetic helium star, with a field strength more than 100,000 times that of the Earth, significantly more magnetized than most stars of a similar size and mass. Therefore, when this star reaches the end of its life and transitions into a pulsar, its already supercharged magnetic field will be amplified by orders of magnitude, to birth the most powerful type of neutron star, a magnetar. The story of these ungodly objects goes back to 1979, when in January, scientists spotted a peculiar source of gamma radiation flashing within the Large Magellanic Cloud, but slightly longer wavelength, so-called soft gamma rays, which soon faded away and evaded detection for a further 2 months. But on the 5th of March that same year, the object returned in the night sky with one of the brightest gamma ray outbursts that had ever been recorded at the time, releasing as much energy in a fifth of a second as the sun in 1,000 years. Scientists were taken aback, and while neutron stars quickly emerged as the primary suspect, both the softness of the gamma rays and their repeating nature demonstrated a phenomenon that was clearly abnormal. By the end of the year, scientists had chanced upon 3 of these signals, which they termed soft gamma ray repeaters, which periodically flashed with low energy gamma rays over the course of about a week, before fading away again for months or even years. But during each's respective flare-up, new light was shed on the underlying power of the objects at hand, as scientists were able to compare their rates of rotation with their levels of spin down to deduce the strength of their associated magnetic fields. And all 3 hinted at field strengths in the order of at least 100 trillion Gauss, perhaps even a quadrillion. So that's 2 quadrillion times stronger than the magnetic field surrounding Earth, and the maximum level of efficiency for a spinning, radiating neutron star. Meanwhile, astronomers had begun uncovering signs of a second type of anomalous, repeating high-energy signal, but this time an X-ray signature. They soon became known as anomalous X-ray pulsars, with a different mechanism driving them to that of a conventional, accretion-powered X-ray pulsar. Scientists quickly noticed that these recurring outbursts of very short X-rays were only a stone's throw apart on the electromagnetic spectrum from those soft gamma-ray repeater emissions the other side of the fence, strongly implying a shared origin. They are both the product of explosions, eruptions, and quakes on the strongest, most magnetic objects in the universe, Magnetars, a term adopted for them in the early 90s. With only about 25 known around the galaxy to this day, Magnetars are evidently much rarer than conventional pulsars, probably because they represent only a brief phase early in the life cycle of the most magnetized neutron stars. But during this brief window, Magnetic reconnection, megaflares, and field decay are all catalysts for some of the most energetic and explosive electromagnetic activity we see from neutron stars. Anomalous X-ray pulsar emissions arise from bursts of photons and flares within the magnetosphere, as well as strong thermal emission from the crust. The soft gamma-ray repeater patterns, meanwhile, are produced by the untangling of a magnetar's supercharged lines of flux, causing starquakes to play out on its surface. As these dead stars rotate, their metallic crusts are tormented on both sides. Underneath by extraordinary electrical currents from the swirling, superfluid neutronium material, and from above by the strain of dragging, twisting magnetic field lines on the surface. Eventually, this crystalline shell is under so much stress that it cracks, a tiny portion shifting ever so slightly towards a more spherical configuration. This adjustment may only occur over a matter of micrometers, but when dealing with a magnetar, even these fine margins are enough to unleash great torrents of radiation, including high-energy X-rays and soft gamma rays. The most extreme starquake ever recorded, as of the timing of this video, was detected on the 27th of December 2004, when the Magnetar 1806-20 released in under 1 second more than 150,000 years worth of solar energy in gamma rays. Despite residing more than 40,000 light-years from the solar system, the trailing shockwaves of this starquake still managed to induce a noticeable effect in the level of ionization in Earth's upper atmosphere. If such an outburst occurred within even 10 light-years of our planet, it would spell the end of most life on Earth. The insane gamma radiation would completely degrade our planet's protective magnetic bubble, allowing pervasive solar radiation to erode the atmosphere's protective layers, boiling away our oceans and rendering the surface of this planet a parched, airless wasteland, bombarded by untenable levels of radiation. And gamma rays aren't the only type of abundant radiation thought to be streaming from the crevices of starquakes. They have also been touted as a potential source of fast radio bursts. Anomalous, short-lived signals brimming with radio noise, for which no concrete theory exists to explain some 700 recorded to date. What's more, is that around 30 of these radio bursts are themselves repeaters. Not regular sources of emission, but recurring nonetheless. And so perhaps they share a similar origin to the soft gamma ray repeater emissions, arising from the quaking shells of magnetars. Alternatively, they may be produced when neutron stars collide, crashing into and consuming one another to facilitate yet more colossal stellar explosions. As we mentioned earlier, the fastest spinning pulsars make for very precise indicators of their surrounding environment. And it was through this method that American physicists Joseph Taylor and Russell Hulse took home a Nobel Prize in 1993. For capturing observational evidence of general relativity at work around the first ever binary pulsar. Their Doppler shift measurements showed a rapidly spinning pulsar, 1913 plus 16, and a slower, cooler neutron star companion sinking towards each other, their orbits tightening as energy was lost from the system, radiated away as ripples in the fabric of space-time itself. A key prediction of Einstein's some 80 years prior. This was the first time that gravitational waves had been observed empirically, but another 30 years would pass before humanity pinned down their first direct detection in 2015, with the Laser Interferometer Gravitational Wave Observatory. When two massive, inwardly spiraling compact bodies draw very close to one another, whether they are black holes, neutron stars, or both. Their gargantuan masses and influences are accelerated to velocities eventually reaching 2/3 the speed of light. This rapid orbital movement of such pervasive gravitational influences raises the space-time around the merger, sending gravity ripples pinging off omnidirectionally for billions of light-years across space, ultimately destined to be detected by LIGO's sensitive array of wave-seeking instruments. The detection of these signals often serves as a precursor for pinpointing the precise location of the cataclysmic event that soon follows. Once a pair of merging neutron stars are sufficiently close, they are accelerated to speeds exceeding their own escape velocities, rupturing their iron shells and briefly exposing their inner contents to the near vacuum of space. A small portion of this superdense material is able to escape, and is suddenly under a fraction of the pressure it was within its progenitor neutron star, causing it to ignite and explode in a tremendous kilonova, as powerful as the strongest supernovae. And like supernovae, the ejector of these explosions is laced with heavy atomic nuclei, intersected by free-roaming neutrons and protons, which combine through the R and P processes to yield troves of the heaviest elements in the universe, from iron, gold and silver to platinum, uranium and thorium, along with everything in between. In fact, it is now generally believed that kilonovae, not supernovae, are responsible for the lion's share of seeding the galactic medium with its heavy, complex elements, including many of the ingredients blended in the recipe for life on this world. And much like exploding stars, colliding neutron stars also produce their own class of gamma-ray burst. Huge explosions of the shortest wavelength radiation, which are seen lighting up the skies of gamma-ray telescopes every other day or so. Longer gamma-ray bursts, lasting anywhere from a few seconds to a couple of minutes, are thought to be the result of supernovae. During a kilonova, on the other hand, the exposure of the shattered neutron star's interiors to space is much briefer, leaving only enough time for a short gamma-ray burst and perhaps a fast radio burst lasting 2 seconds or less. Almost straight away, the debris from both bygone neutron stars is lugged back in to form a new composite object, which itself undergoes a gravitational collapse under the same conditions as before. If the combined mass is above 2.5 or 3 times the mass of our Sun, then the bodies will form a new black hole. Below the threshold, they will simply reconvene into a new, heavier recycled pulsar, or perhaps a magnetar, restarting its evolutionary cycle. The question is, what if the combined mass comes in right between these two eventualities, where the compression is substantial enough to overcome the force exerted by neutrons, but not quite significant enough to compress beyond the radius needed for an event horizon? You would wind up with a boundary object, a collapsed star so dense that even neutrons come unbound into their smaller subsets, under conditions so extreme they resemble those of the early universe. Protons and neutrons, the two particles comprising the nucleus of an atom, are both types of hadrons, a class of subatomic particle composed of 2 or more quarks. Quarks are a type of elementary particle, in that they have no further subsets that pressure or heat can split them into. They are the tiniest pixels of mass in nature, and were the first kind of matter to form in the young universe. We don't see free quarks in the wild today, however, as creating quark matter analogous to neutronium requires unfathomable temperatures and densities, even greater than those found in a neutron star. In fact, the last time such conditions existed was only just after the universe's inception, when its entire contents were crammed into a comparatively minuscule area, packed even tighter than the nucleus of an atom. An ocean of primordial quark-gluon plasma permeated all of space, oozing with the essence of the strong nuclear force. But over time, space expanded, and this ocean spread out, cooling and condensing into hadrons, followed by other, larger aggregations. And ever since, free quarks have not been seen in nature. But if a newly formed, accreting neutron star treads the fine line of the Tolman-Oppenheimer-Volkov limit for a black hole, a certain borderline mass may induce the kind of gravitational collapse that can overcome neutron pressure to achieve quark deconfinement. Neutronium would be broken down into an even more compressed and energetic quark-gluon superfluid, held apart by its own, even stronger nuclear repulsion against gravity, giving the dead star the density of a large hadron, as opposed to a large atomic nucleus. Such an object is known as the hypothetical quark star. They are to quarks what neutron stars are to neutrons, smaller, even more compressed spheres of quark-gluon matter, which would likely appear similar to a neutron star, albeit with its own unique set of emissions. If a quark star is two-flavor, consisting entirely of fundamental, first-generation up and down quarks, then it may appear very similar to a neutron star indeed, consisting only of a quark-gluon core concealed by layers of less pressurized nuclear matter, with a maximum diameter of about 15 kilometers. On the other hand, a quark star could be three-flavor, containing an almost equally balanced number of up and down quarks, alongside heavier, second-generation strange quarks. Strange quarks are one of 6 types in total. They have the same charge as down quarks, but can be converted into up quarks via the agency of nuclear forces, and thus their presence would drastically alter the recipe for a quark star, making it significantly more stable in low energy states. In fact, strange quark matter may be the one true ground state for mass at the highest densities, and has been described with many different mathematical frameworks as being both perfectly stable and everlasting. As such, a three-flavor, strange quark star with strange matter in its interior is inherently self-bound, and may not even require a solid nuclear surface binding it together as a result. It may instead have a transient surface, playing out a volatile cycle of emissions we could potentially detect from the Earth. In the beginning, a strange star would have no solid surface, and would instead be defined by a boundary where quark density abruptly reduces to zero. But over time, blistering electrical currents from further down would force any surviving scraps of normal nuclear matter outwards, collecting just beyond the edge of the quark matter into a tangible, decoupled, scarcely stable crust. This surface would be extremely short-lived, before long collapsing back into the strange star to catalyse a plethora of gamma-ray emissions, which has been touted as a possible explanation for so-called anomalous soft gamma-ray repeaters, which show departures from conventional magnetars. Thereafter, the bare, chaotic strange quark interior would once again be exposed to the cold expanse of outer space, and because strange matter is thought to be so stable, any that is lost from the body during this cycle of outbursts would likely maintain its ground state, manifesting as a particle-sized nugget of strange quark matter, known as a strangelet. If such a stray, free-streaming nugget entered a system with more conventional celestial objects, such as ordinary stars and planets, then instead of losing its state or exploding on impact, a strangelet may instead contaminate its impactor and pass on its ground state properties, dissolving the structures of atoms and reducing them to strange quark matter, ultimately inducing a snowballing process that causes the body's collapse into a strange quark planet or strange quark dwarf. Though the long-term stability of these middle-range mass objects is still very much up for debate. Either way, with no means to distinguish them from conventional pulsars, theories on quark and strange stars can be viewed as little more than speculation for the time being. For now, they remain firmly in theoretical realms. They have been predicted and described with mathematics, but never reflected in reality by observations. However, there is one more type of, so to speak, hybrid neutron star we've not yet covered, which not only may be possible, but might even have occurred within our own cosmic backyard. GRO J1655-40, formerly X-ray Nova Scotia 1994, is a 10,000 light-year distant chaotic binary system, hosting a small evolved F-type star which is losing gas and matter to an unseen, accreting companion, inferred to be a black hole several times the mass of the Sun. These objects orbit one another at considerable velocities, suggesting they were born with this momentum from the same progenitor object, a hybrid star which itself was the product of a neutron star going rogue in a binary system. Only this time, the companion was not a dwarf star, but rather a gigantic, radiating red giant, far too large to be ripped to shreds when its decaying orbit brought it within range of its neighbour. Instead, the inwardly spiralling neutron star would have plunged beneath the outer layer of the giant's photosphere to create a Thorne-Zytkow object, a star within a star. First conceptualized in 1977, a Thorne-Zytkow object is a red giant that has swallowed its neighbouring neutron star, which then spends the next few hundred years swirling in towards the giant's core, lugging its magnetic field and gravitational influences through the plasma and disturbing the internal structure. From the outside, such an object would not look much different to an ordinary, evolved red giant. In fact, most of the candidate Thorne-Zytkow objects tabled over the years have turned out to be late-stage, asymptotic giant branch stars. But inside one of these hybrid stars, chaos would ensue as its internal structure is unhinged, the core itself pulled into orbit around the neutron star. These objects would circle each other and draw closer, before merging and gobbling up most of the star's interior into a newly formed black hole. But beyond the bounds of its event horizon, great swathes of the now hollowed red giant's layers would remain. And it is this leftover material that is thought to have condensed to form the curiously unmassive F-type star which circles and feeds the black hole to this day. It just goes to illustrate how much can arise purely from the discord unleashed by these cosmic hellscapes. Despite their tendency to pulverize their surroundings, the pervasive influences of neutron stars have still made seminal contributions in tending our galaxy, and priming it with the ingredients for life, therefore single-handedly dragging it into its inhabited era. And when you look at it like that, their discovery has been every bit as important to science as it would have been if the LGM-1 signal really had turned out to be a one-off from aliens. And with that, I bid you good night. C signing out.